All right, so it looks like this morning's been a morning of stack-based languages. I have another stack-based offering. My name is Clayton Bauman, and I'm the author of the Babel programming language. Today I want to explain to you how Babel works, as well as to demonstrate the language to you using the reference implementation that I've been developing. I began developing Babel around 2006. There had been revelations in 2005 that the NSA was routinely spying on US citizens. At that time, many privacy rights observers were concerned that those revelations were just the tip of a much larger top secret iceberg. And in the last few months, we've gotten a better idea of just how large that iceberg really is. What is the connection? Well, the security flaws, which we now know that NSA introduced into many devices and protocols which we all use, were made possible in large part by a flawed legal model of property rights in these devices. Unfree software, proprietary hardware, digital rights management, and government backdoors make possible malicious features that are opposed to the rights of the user in his or her device. I want to assert that today we have an inordinate focus on the rights of the designer in his or her design. And this is particularly true in software, where the product is the design. Instead, I believe we need to shift our focus to the rights of the device owner in the use of his or her device. And this is the message that Richard Stallman has been repeating to the world for decades in regards to free software. Babel is a general-purpose, high-level language, and you might wonder what these lofty political and ethical concerns have to do with designing a programming language. And my view is that they have everything to do with it. If I truly own my Android or my iPhone or my Windows 8 laptop, then I should have every right to crack open the case, change out the BIOS, and put whatever software I want to run on it. But if all manufacturers can and do dictate to me that I will use the software that is pre-installed on their device, whether or not I trust that software, then all devices become vulnerable to the widespread security failures, which we have learned just a couple weeks ago that NSA and GCHQ have foisted on the digital community. Babel 1.0 will use public key cryptography to permit the interpreter to check whether a given piece of code is permitted to run locally. And this changes the way of thinking about rights and executing code on a device. Rather than asking what software is this device permitted to run, we are asking what software do we trust to have access to this valuable device's data, resources, and execution capabilities. Now, to be clear, code authentication is not a magic cure to security flaws in the underlying platform. If the underlying platform is insecure, then the interpreter cannot possibly hope to be secure. However, a large community of users can push proprietary platform vendors to get with the program, that is, open up their designs to verification and thus become trustworthy. And even though I've talked quite a bit about security concerns, I want to emphasize that Babel is not a domain-specific security language. Rather, Babel 1.0 is a general-purpose language with a large set of security primitives built in as operators in the language, as well as the interpreter will be able to perform cryptographic authentication to permit remote code execution. So, despite my nervousness, I want to jump into the details of the Babel language and then give you a demo so you can see Babel in action. So the preliminaries are that Babel is a general-purpose, high-level language. It is a stack-based language, as I mentioned earlier. So that means we're in postfix order. So instead of saying the more familiar, var equals 1 plus 2, we're saying, put var on the stack, then put 1 on the stack, put 2 on the stack, perform the plus operator to add the 1 and the 2, and then perform the set operator to put 3, the result, into var. Babel is not pure. Many operators can have side effects, and Babel is untyped. This is probably the most controversial part is being untyped. But we do have tags which allow us to keep track of types if you want to. So the Babel data structure is called the B struct, or for Babel struct. It's the underlying container for all data in a Babel program. And data such as strings, integers, unsigns, floats are all stored as values in leaf arrays. And no pointers can be stored in a leaf array. So that's one kind of thing, is the leaf array. Ordinary pointers are stored in interior arrays. Every pointer in an interior array must be initialized and valid. A valid pointer is a pointer that points at the first entry of either a leaf array, an interior array, or a tagged pointer, which I'll mention in a moment. And no values can be stored in an interior array. A tagged pointer is a pointer with an associated 128-bit hash value called a tag. So these three items here, the leaf array, the interior array, and the tagged pointer, are what define what compose the elements that compose a B struct. And a B struct has a single root pointer. All right, so to associate syntax with what's being encoded internally, this is a fairly low-level view. We're actually looking at what are the words. If you're in a 32-bit machine, this will be 32-bit words. Or if you're a 64-bit machine, it'll be 64-bit words. What are the words that we're actually compiling? So this is almost like a bytecode view. If we say val on the left and give 3 hex values, I used hex because the dumping operator dumps out the view of memory in hex, so we can visually correlate it. Give it 3 values, we're going to get an array of 3 values. If we say pointer and give it a list of 3 values, we're going to get an array of 3 pointers pointing at single value arrays. Pointers, unlike values, can be nested. Pointer arrays, or interior arrays as I called them. And here on the top line you can see an example where we have a pointer to the value ace, and then the remaining points at some more pointers, which is equivalent to the list syntax shown below. So both of these will produce the same memory image, which you can see illustrated with the picture here. The interior arrays or pointer arrays are encoded in green, and the value arrays are encoded in blue for differentiation. And then the tagged pointer, which I mentioned the last item, is basically a way to take some string description and associate it with a pointer. And here we have a tag statement, and foo being the string that we're going to hash. We're going to convert it into a 128-bit hash. And then we're going to point to whatever comes after that. So in this case, we've taken a foo, we've hashed it, and it's now pointing at the list that I illustrated to you before. And so you can see in this slide all 3 elements together, the tag, the interior array, and leaf array. And then this is the code statement shown in the sparse syntax. I'll mention that in a little bit. And you can see that code is data in Babel, which is nice, because we can just put anything we want into a code statement, and it will be assembled by the parser, compiled by the parser. And then to emphasize that Babel is untyped, here I've shown 2 different syntaxes that compile to the exact same thing. So if we have val and you give the string hello, you're going to get these ASCII bytes out shown on the right. And if you take the same hex bytes and you say val and give those hex bytes, it's going to give the same thing. Okay, so the underlying virtual machine, or the BVM, Babel Virtual Machine, is stored in a B struct or as a B struct. It consists of 3 stacks. It has a down stack, an up stack, and a managed stack, which is a hat tip to Chuck Moore, named it R stack. Code list is implemented as a linked list, and it contains data operands and code or operators, or a mix of both in reality. And that's pointed to by the code pointer. Every data operand, as it's encountered in the code stream, is pushed onto the D stack for later operation. And then there's a kind of stack nesting. I think it's unique to Babel. Using these operators I call up and down, we can avoid some of the need to rotate and do other things to the stack with these operators. Conditional looping and other operators that manipulate code pointer utilize the R stack. And the symbol table contains all symbols. And these are the primary elements that are going to make up your Babel Virtual Machine, your BVM. So the runtime, or Babel interpreter, actually has a small bootstrap, and it's self-written in Babel, and it loads your Babel program for you, and you can inspect these 3 files here in the source directory to see how that's done. Actually, when I run the make script is going to take these Babel files and it's going to write a C file out and then compile that together with the Babel interpreter. It maintains a cache copy of the most important pointers to avoid needless traversal of the BVM. For example, code pointer, as you're executing your code, you don't want to be starting from the root pointer of your virtual machine, traversing through to the code pointer. So we actually maintain a cache of that internally. There's a jump table that permits OV1 vectoring to built-in operator functions. We just have a function pointer array, the opcodes indexed into that array, and we jump to the function we want to execute. And then there's the interpreter is also responsible for command line capture, pulling in the argvs, standard in, environment variable capture, etc. Okay, the reference implementation is written in C. It has a Perl wrapper front end right now that generates the native Babel binary for me, and a little Perl script called sparse.perl, which stands for S-expression parse. And it has a minimal syntax for the immediate values, so we can take everything and compile it into the Babel Virtual Machine bytecode. And then optimizations will begin after I get to Babel 1.0 someday. Okay, so here's a big picture visual view of what I just explained to you. It's a little bit small on the screen, I apologize, but on the left we have sort of the world out there. We have I/O between the Babel interpreter, which is depicted as the code, or the little cloud there in the center. And then above and below that we have the up stack and the down stack, which allows us to move up and down the stack. I'll illustrate that to you with a demo. As well as we have a symbol table to keep track of symbols, persistent symbols, the code stream going off to the right, and then the R stack to manage our control flow transfers, as well as mass storage for file accesses. What is the future of Babel? So I'll have a built-in parser at some point for a syntax that I'm calling bipedal, which will be kind of, a superset of the sparse syntax that we have right now, which is kind of everything has to be written in S expressions. I'll have a wide selection of crypto primitives built in from the libtom crypt, as I mentioned in the introduction. And it will also be linked with libcurl so that we can pull in and access the web, web get and put. bzip2, so we can actually have some compression operators that just work right in with the language, as well as graphiz. I hope to link that in. I'll actually have that as part of the demo so that we can actually see what is going on inside the interpreter. And I hope to get it compiling on GCC and MinGW in the future. Right now it compiles on TCC, which is not widely used compiler. And I expect to make it cross-platform compatible on Windows and StarNext platforms to start with. We'll have also additional built-in operators which are not currently in. I have about 250 operators right now. I'll probably top off around 300 or so at 1.0. Okay, so the meat of the presentation that I want to get to is just sort of to demo Babel to you. I apologize, my screen is a little bit narrower on the presentation display, so there may be a little bit of crowding as we switch back and forth between the demo view and the command line. Okay. So, all right, so let's say we wanted to write a hello world. We're going to actually do some live code editing. I just wanted to up the pressure here. And bigger? Well, I won't be doing it here, so let me see what it looks like in Vim. Is that readable? Okay, well, let's see if we can do it. All right, so I'm going to create main. I hope that's readable, at least in the back. I apologize if it's not readable. So first we're going to create a list here, main, put main in it, and we'll say hello world. And we now have a string, and we're going to print the string out. This is very, very scary, very difficult stuff here. And let's see if it works. Okay, there we go. We got a hello world. Okay, and then let's add some numbers together. We can do some other interesting things. very difficult, complex things like adding some numbers together. Again, we're postfix order, so this will be 2, 2 plus, and that should give us 4. We'll convert it to ASCII form, and then we'll add a new line and we'll print it out. Okay, let's see what we get here. And we got hello world, and 2 plus 2 does in fact equal 4. Let's see, what else can we do? We can make a list of names here. And some good names here. These are good names. And let's say we wanted to print these out, each one on its own line. So we'll give a new line, and we'll print it out. And then we just say each, which is a lot like a map operator that was mentioned earlier. And let's run this and see what we get. All right, looks good. We got our names printing out here in the back. For the people in the back, it is actually working, if you trust me. And then what else could we do? Let's see. Let's try some 3 random numbers, and these will actually be in an array. So we'll say each array. So it's going to print out each element in the array. And let's make them between 0 and 99. So we'll do remainder, and it's reverse order because we're stack based here. Then we'll convert to ASCII, we'll add a new line, and we'll print it out. So we should hopefully get 3 random numbers in addition. There we go, very good. And now let's say for just no reason at all, we just want to do all of this stuff 3 times. So we go ahead and put everything in a code list, and we just say 3 times. And then we'll actually give some space here so we can see. We run it, and there we go. We've printed everything out here, same as we had before, but 3 times. And the numbers generated are random. I'm using Mersenne Twister for the random number generator. Okay, so what is going on underneath the hood? What is actually in hello.sp once it gets compiled by the parse script? So let's actually, I have another demo program, which I want to show you. bstruct.sp, and what this is actually going to do is it's going to pull in on the command line, whatever we give on the command line. It's going to read the file in. I just called that operator slurp in honor to Perl slurping. We're going to load it, which is actually taking the array of bytes that we read in, or actually words, and then making them live in the Babel program. And then we're just going to do this magic little thing I call display here, which is going to pull it up and display the view for us. So let's run that. And .sp, and we'll run it on the hello world program that we were just taking a look at a moment ago, hello sp.bbl, which is the compiled version of it. Whoops, you can't actually run that, have to run Babel. And let's give it a moment to process. So what this actually shows is this is a view of everything that is in. And I know that's too small to read, but I'll just zoom out so you can get a view of the scope of the hello.sp. So after hello.sp, which is everything that we were just editing live on screen a moment ago, has been parsed by the sparse.perl script. It spits out the bytecode, and once we read the bytecode in Babel, this is actually what it looks like. And you can see the various elements there. Here's the the tag pointers, the interior arrays, and leaf arrays are depicted here with the bold boxes. Okay, and we'll take a look at a couple more after this. First, I want to show what is going on in the stack, because we have, in a stack-based language, we're operating on the stack all the time. So what is actually going on in the stack? So we have 2, 3, 4, and 5, just 4 operating values. We're going to push these onto the stack. Then we're going to put the stack pointer itself on the stack, and we're going to display what does the stack look like. So demo/ud stacks.sp. All right. So we're going to run this, and hopefully we see something like what we expect to see in the stack. So here we have the 2, the 3, the 4, and the 5, and you can see 5 is on the top of the stack. It's the last thing that we pushed onto the stack. These zeros here are kind of a stack indexing metadata, which will have tags associated with them later on. It's unimplemented, so just ignore those. All right, so the up and down operators, which I mentioned earlier, mysterious operators, I'll just show you how those work to help simplify stack usage. So the easiest way to explain it is just to do it. So 2, 3, 4, 5, and then we're going to move down the stack 1. So we'll rerun here and see what does our stack look like after doing a down. Okay, so now we just have 2, 3, and 4 on the stack, and what we've done is we've just removed the 5 off the stack, and let's see how do we get the 5 back onto the stack. Is well, obviously we use the up operator to get the 5 back up on the stack. So let's rerun there and take a look at what we get. Helps to go over here. Okay, so now the 5 is back on the stack. So 2, 3, 4, down, back up. We've gotten our 5 back. So essentially the up and down operators are just implementing a second stack, which is what the use stack is for. So we'll take a look at the use stack after we've done only a down and not an up. So we're going to do 2, 3, 4, 5, move down, and let's take a look at what's on the use stack. And hopefully we see there what we expect to see. And for some reason, it's not popping up now. And there's our 5. So the 5 was just moved over to the use stack, saved over temporarily. OK. All right, the next thing to show is the symbol tables. So we'll take a look at the symbol table. OK, so I've prepared a little program here that's just going to, first time we're going to do 2 things. So first we're going to do program A, and then we'll do program B. Program A, we're going to put the pointer for the symbol table on the stack, and then we're going to just display it and see what's in the symbol table. Whoops. Hold on, typos. OK. And this one will take a moment to process. And it appears that there's nothing here. There is actually something here. It's just fairly big. So just got to zoom out. And here's a view of everything in the symbol table right now. So why is there so much stuff in the symbol table? We weren't putting anything in the symbol table. We're pulling in the environment variables. And this big guy hanging right here, all of that's our environment variable been read in. OK, so the next thing that I want to show you on that symbol table is we'll run program B now. And what this is just going to do is say, let's look up the symbol environment. And this operator is just a development operator. It's actually going to go away fairly soon. But let's look up the env symbol, and then let's look up path in that, and let's print it out. So I'll rerun that command. And we should see this time. There we go. So we've printed out the path variable. We've read it in from the environment. Yay. Complicated stuff. All right, so what else? Let's take a look at hashes or hash tables. We have arrays of values, arrays of pointers. We have lists. What I haven't shown is the hash tables, which are responsible for implementing the symbol table. I will not be able to show both of these together because the screen has been made narrow. But here we have a list of plural animal names in their groups, like you usually see in a textbook. And what we're going to do is, actually I'm going to change this right here. OK, we're going to take this list of lists, and then I wrote a little bit of snippet of code here called make hash, which is actually in the same file down here, make hash. And what make hash does is it declares a new hash for us, and then iteratively inserts all those elements into the hash for us. So we're going to make the hash, and then we're going to perform some lookups in the hash. So /hash.sp. Okay, so this part, I apologize if you can't see down at the bottom, but if I type, eagles, it gives me Irie, which is the plural, I guess, for eagles. And then trout, oops, it's going to crash if you mistype. If we type trout, we get hover, and so on and so forth. Cattle, we should get herd. All right, so it's looking up in the hash. All right, so the next thing I want to show you is loops or error control or flow controls, excuse me. So let's take a quick look at loops. Okay, so I have various loops. We can do times. We can do loops, loop, which is loops indefinitely. Do while loop, and then I'm going to do a demo of a Cartesian product with two nested loops. So what I'm showing here is I'm taking that same list of lists construct that I had before mapping the strings into the hash, and I've just mapped in pointers to the code snippets themselves. So it's actually a hash that is pulling up code for us, and then we can eval the code. And this little exclamation mark guy here is my clever way of saying eval. I just shorten it. It's like do it, imperative. So let me just illustrate loops. So we do Perl Babel demo / loops.sp, and we'll say loop, and that's going to look up the code for the loop for us, and it's say 10 times. Okay, so 10 times it runs this subprogram for us that it pulled up using the hash, and iteratively prints out the stars. It's counting up from 0. Because loop operator goes indefinitely, so it just counts up 0, 1, 2, 3, 4, 5, 6, and so on. If we wanted to do a times loop instead, we can say times here to this little demo program. It's going to go and look up in the hash for us, and it's going to do it 10 times. And this time we'll see that the stars are counting down. That's because the times operator operates on a countdown, 10, 9, 8, 7, until it gets to 0. Okay, and then I'll just quickly demo the Cartesian product, and this one I'm going to turn down from 10 to 3 because you get the square. And this just illustrates we get 3, 3, 3, 2, 3, 1, 2, 3, 2, 2, 2, 1, and so on and so forth. And that's just implemented using this nice little operator here. Let's see if I can show it. This iter operator. And what the iter operator does is it goes and pulls whatever current iteration count I'm on so that you have access to that. Which is better than, I think, than C for loop where you have to manually track it. Okay, so the next thing I want to take a look at is copying, which I think is a very important point. A lot of the stack operators in Babel are inspired by Joy. I think Joy is a very beautiful language. I'm sure a lot of people here agree. Unfortunately, it's not being developed further with the passing of Van Thun. But here we have a list of lists containing characters, and we're going to put them on the stack, and then we're going to dupe it, and then we're going to display the stack as we've done before. And we'll just take a look at what does that look like. Does it look like what we expect it to look like? Maybe, maybe not. Okay, so I'll just zoom out a little bit here. And what we see here is this stack view might be a little bit confusing. This is the top element of the stack right here, and this is the top of stack -1. It's the next thing down on the stack. And what you see is that they're both pointing at the very same list of lists here. And here's our list of lists depicted for us with all the const boxes. A little bit busy, but I think we can see what's going on there. And then by contrast, let's take a look. If we change this dupe operator, we change this to copy, and now we're going to rerun. What changes? All right, so the view here is a little different. Now, here's our top of stack -1, but instead of pointing at the same items in memory, we actually have 2 full copies in memory of the list of lists that we created to begin with. So the copy operator just does a by-value copy for you in place, and it's very efficient copying of, and this can be applied to arbitrarily large data structures. Okay, so let's take a look at unload demo now. So the unload operator in Babel, it's kind of half of copy. And what it does is it takes a list of lists. We're going to create this hash out of it. And then we're going to unload that hash, which is actually going to serialize the whole data structure into a single array. And then we're going to come down here. We're going to spit it out to this file, demo.unload.babel. So I've serialized the whole data structure, and I'm going to put it into file. So let's run it, Perl. And it won't actually do anything very interesting. It'll pop up and show us. Okay, so these are the first few bytes of the array being depicted there, so you can see it. And I apologize for the screen being a little too narrow, but we'll take a look at that file that got dumped out. So we'll look at the hex values here, and we'll just scroll up to the top one. And you'll see here that the first two 16-bit words are 0, which we would expect here given the display we've been given. The next 16-bit word is BFE8, which is the lower half here, and 93.5, which is the upper half here. It's kind of a little Indian, of course, Intel, and continuing on from there. So we can see that these bytes have been spit out as exactly as we expected into file. So the other half we want to look at is the load operator, which kind of undoes unload. So now what we're going to do with this demo is we're going to actually open the file that we just put out. We're going to pull it in, and we're going to invoke the load operator on that to make that data structure live in memory. So okay, so what we've done, and we're at that same prompt that we had before with the hash demo, hash.sp, and it's asking for a key. If I type in, for example, cattle, it comes back and says herd. If I type eagles, say eyrie, trout, say hover, and so on and so forth. Geese should give gaggle. And what's different about this time running is that instead of getting the hash, having written out the hash in this SP file, what's actually done is it's pulled in the serialized version from that unload.bbl, loaded it into memory, and now we're able to operate on the hash that we've loaded from file. Okay, and now I'll give my final demo and then take questions and answers. Okay, so I have a little program here that I called babel.sp, and what it's going to do is take whatever we give it on the command line. It's going to pull it in, slurp it in, load it. It's going to print dream. Then it's going to execute what we pulled in from the command line, the file that we pulled in, and it's going to print dream again. So we'll say babel demo/babel.sp demo/inception.sp.bbl, and it prints dream within a dream. So let's take a look quickly at what is in inception.sp. And we'll see within a here. So what has happened is we've actually pulled in a Babel program that was earlier compiled. We've loaded it, and then after printing dream, executed it, returned, and printed dream again. That's all I have. Take questions.